Okay, recording. So 10.5, the ratio and the root tests. So we're looking at series such as the one here given is 1 plus 2 over 1 factorial plus 2 squared over 2 factorial, etc. They come up, the convergence tests so far cannot be applied that easily. So these couple of tests that we're going to look at today are an alternative that are pretty easy to look at. And they make a ton of sense, at least to me. So theorem 1, the ratio test, assuming that the following limit exists. The limit as n approaches infinity of absolute value of a sub n plus 1 term over a sub n term. So write the next term over the previous term. So if that limit is less than 1, then the series converges absolutely. So I interpreted this as implying that if our ratio turns out to be less than 1, the absolute value of it, then the sequence, why is this page moving on me? The sequence is then decreasing.
On the third root is, I'm sorry to interrupt.
That's okay.
Is there any way that you could focus the screen just a tiny bit better? It's quite hard for me to read.
How's that? Any better?
Yeah, that's much better.
Excellent. No need to apologize. Okay, so sequence is decreasing then. It's implying that if we're less than 1, then the denominator is larger. So the previous term was larger. If the limit is greater than 1, it diverges, which also implies that the sequence is increasing. So that's how I interpreted this, and I found it to be pretty helpful. The third scenario, right, of course, it could equal 1. The ratio could be 1. Then, therefore, the test is inconclusive. We could have a convergence or a divergence. We would have to do something different with that. And we'll go through examples that show each of these, as well as what happens if it's converging or diverging, and what does that look like? Where's one that gives us this result, but yet we have two different things coming from it? Okay.
I wasn't copying down.
There you go.
Thank you.
Yep. I'll pause the record. So first example, prove that this. Go back.
Sorry.
Yep. So our first example, prove that the sum from 1 to infinity of 2 to the n power over n factorial converges. So in order to prove this, we need, for the ratio test, we need the n plus 1 term and the nth term. So I am creating absolute value of a of n plus 1 for n. That's what I'm looking at. So if I take a look at the a sub n as it's presented in the summation 2 to the n power over n factorial, I know that that numerator is going to become 2 to the n plus 1 power divided by, now I need kind of a clever way to come up with what n plus 1 factorial looks like, because I do want things to cancel out. So the idea of factorial, right, is you just keep on multiplying, obviously, each term. So I could say, well, the n plus 1 factorial is equivalent to n factorial times n plus 1. Okay. So that's my numerator. And the a sub n is then just 2 to the n power over n factorial. I rewrote it, why not, just to clearly see the multiplication of the reciprocal, just to, again, show exactly how it cancels. So I'm now multiplying by n factorial over 2 to the n power. Okay, so this allows me to really see exactly what cancels, what simplifies. So obviously the n factorials are gone. That's the obvious one. But the 2 to the n plus 1 and the 2 to the n can simplify as well. Same basis, separated with division. I'm just going to subtract those exponents, so the n exponent goes away. And I'm left with, in the numerator, a 2 to the first over an n plus 1. Okay? Really maintaining my absolute value the whole time, but we're fine because n is starting with 1. So now I just want to take the limit of this. So the limit as n approaches infinity of this 2 over n plus 1, well, my numerator is going to grow without bound, so therefore this limit is 0. Right? So if the limit is 0, then this series converges.
Absolutely.
Yes.
You can
by
just
the
say
ratio
it
test.
converges too, right? Since if it absolutely converges, then it converges.
I mean, it
Yes,
could also
yes, there was
converge
that
from this-
implication,
Yeah.
correct.
You should probably specify.
We should specify, but what he's referring to is, without, I don't want to stop my recording. In 10.4, absolute convergence implies convergence. So he's not wrong there with the assumption. So we are proving absolutely because that's what this theorem says. But there is the theorem in 10.4 that it's theorem 1 in 10.4, absolute convergence implies convergence. So we're okay there. But in this section, I'm just going to state exactly as this theorem is presented. Okay. So our second example, am I okay to move on? Okay.
I believe so.
All right. Spokesman Simon, appreciate you. Example 2, does this series converge? And now we have an n squared over a 2 to the n power. Same process for this. Right, I'm coming up with my n plus 1 term over my n term. So I would have n plus 1 squared over 2 to the n plus 1 divided by n squared over 2 to the n. I'll put the absolute values for the definition. And this is equal to n plus 1 squared over 2 to the n plus 1 times 2 to the n over n squared. Simplifying. The 2 to the n simplify in the same way, so I'm just left with a 2 in the denominator. So I have an n plus 1, which we could FOIL out. It's okay to accept. We know that the leading term has an exponent of 2. We know that the leading term does not have a coefficient, but if you wanted to expand it, there's nothing wrong with that, of course. So it would expand, obviously, to n squared plus 2n's plus a 1 over, we do now have a 2 left over in the denominator, which is very significant in terms of the limit, because now when I take the limit of that, and I'm taking the limit of, again, the definition would be written as a sub n plus 1 over a sub n. In this case, the limit is equal to a half. We care about the fact that 1/2 is less than 1. Right? So
it
now,
converges absolutely.
exactly. So by ratio test, it converges absolutely. All right, so now I'm going to show you, the next example is a divergent, or it does not converge, so therefore it diverges. So we have summation 0 to infinity of negative 1 to the n power, so we are alternating, times n factorial over 1,000 to the n. Okay. So same process here, right? When I first went into this, I said, well, I'm going to take the a sub n exactly as it is. But because we do have the absolute value, that negative 1 to the n power is not relevant because we're putting it in the absolute value. All that does, remember, is it alternates signs, positive, negative. But we are looking at the absolute value of the ratio. Therefore, we only have to be concerned with the n factorial divided by the 1,000 to the n for our a sub n term. Okay? But I'm going to put it in there just so that we recognize that, yeah, it's obviously part of this series. And remember, when you're doing an n factorial with respect to n plus 1, treat it as n factorial times n plus 1. Over 1,000 to the n plus 1. And this is all over negative 1 to the n. Then we have our n factorial over 1,000 to the n. So when I simplify, I'm just going to drop the negative 1 part because that's the part that would go positive. And then I'll multiply by the reciprocals and see how things cancel out. So we have n factorial times n plus 1, 1,000 to the n plus 1 times 1,000 to the n over n factorial. Right, and now that that alternating part is gone, the absolute value is not necessary any longer. So my n factorials cancel. My 1,000 will remain in the denominator as a 1, to the 1 power, I mean. So I have an n plus 1 divided by a 1,000. Okay. So when I take the limit of this, as n goes to infinity, right, it goes off to infinity. My numerator degree is larger. Therefore, which is greater than 1, that's the only interpretation that we need, therefore it diverges by ratio test.
I have a question.
Okay?
So for the factorial on the top left,
Yep.
so it was, you wrote n factorial times n plus 1. So why isn't that like n plus 1 factorial?
It's just a clever way so that I can cancel that n factorial out. If you're comfortable saying the whole thing is n plus 1 factorial and then understanding how to cancel the n factorials out, then you're fine. But defining it initially as an n plus 1 factorial is the same as n factorial and then one more after that. That allows us to clearly see that it's going to cancel. Because if I don't cancel, doing this limit, is not really as easy. All right, so last example, the ratio test. And this is the one that's going to be inconclusive. So we're going to show that both convergence and divergence are possible when that limit is equal to 1. And we're going to do so by looking at the series with n squared and the series with n to the negative second. Right, by just looking at the n squared, we know that that's going to go off, right? That's going to diverge. It will not stop at a certain value. And the n to the negative second, we already know that also, that one converges by the p-series, right? It's greater than 1. So let's take a look at how the ratio test gives us the same result here, but obviously the final answer is different for each of them. So the ratio test, I'll do the left side with n squared and the right side with n to the negative second. So if a sub n is equal to n squared, then we would have n plus 1 quantity squared over an n squared. Let my back just so I don't like that choice. And that would simplify if we needed to expand it to n squared plus 2n's plus a 1 over an n squared. Absolute value, but it's not necessary based on what we have here. Okay? So if I took the limit of that, our degrees are the same, so we would get 1. And which is then inconclusive. For the ratio test. Okay. And then on the other side, if I went through the same work, I would start with an n plus 1 to the negative second over an n to the negative second, which, with those negative exponents, I just flipped it right off the bat. So then I have an n squared. I don't need the absolute value because we have quantity squareds. N plus 1 squared. So obviously we're going to have the same result, but opposite numerator and denominators. And therefore my limit would again be 1. So inconclusive also. But this series is convergent by the P series, because P is, well, when it's flipped, right, it's greater than 1. Let me actually write it. That's how I would typically write it. So 1 over n squared, because P is greater than 1. And then over here, we could use P series as well. I'm just going to claim that it's divergent. I think we're all comfortable with that one. But if I did flip it, then P is not greater than 1. P is less than 1 because it would have a negative exponent, and it would be divergent as well. Okay?
Wait, what do you mean by flip it?
If I wrote it as 1 over n to the negative second, so then I could compare it as the P series rule.
Oh, yeah, true.
Okay. All right, so the other test in this section is called the root test. And this one we're going to use, typically if it starts with some outside exponent, right, in that first example, as you can see there. And the root test then allows us to take the nth root of the absolute value of a sub n, and if those powers and those roots cancel out, then we're left with that fraction that's there, or something along those similar lines. And we can do similar logic where now, okay, if the limit is less than 1, then the series is going to converge absolutely. Right, because that fraction is less than 1, and a fraction raised to an exponent without bound would zero out. If that fraction has a limit greater than 1, then it's going to diverge, because now you're taking a value right here that's larger than 1 and raising it, so it's going to diverge. And if it's 1, again, it's inconclusive, same idea. So it's really looking at almost the same thing. It's already, in this case, the particular starting as that fraction. We're just trying to get rid of this guy. So if we can take a look at just what's happening in this fraction, it kind of is a ratio test happening, because we're just looking at, is the numerator or the denominator greater? So it goes to the limit at infinity. Okay? So this first example here, right, just has us saying, well, what's that limit as n approaches infinity of the nth root of the absolute value of this? N over 2n plus 3 to the nth power. So of course our nth root and our n powers cancel out. That's the point of it. We still have our absolute value. And in this case, our degrees are the same. So this would equal a half, which is less than 1, which implies convergence, absolute convergence. By the root test. Okay. So 2 more tests to add to your list. When I've been meeting with a couple of you here and there, I get this. It's tough. It's tough on me. It's tough on you guys. We're all first timers with these topics. I think honestly, as this chapter moves forward and you're given more flexibility of which test to use, that's actually helpful. When you're told, no, you got to use this one, Sometimes it feels forced, even though you have an understanding of, I'm pretty confident that it's going to converge or diverge, but now how do I prove it using this test? So, when you get to that end game where you're not being told you have to use this method, I think that you'll find that these problems are quite logical when it comes down to it, and you can kind of, figure out, again, it's most basic of, is it going to grow forever or is it not? Is it going to go to some value? Is big picture coming out of this chapter. Obviously, there's a lot of little things along the way. Let me stop recording.